Hello there, and welcome to Simple Sleepy Science. Tonight, we drift into the most peaceful place in existence. Space. The infinite void above your head right now. And it holds something you've never truly experienced. Complete silence. Right now, just beyond the thin shell of atmosphere wrapping our planet, there exists a quietness so total, so absolute, that nothing on Earth comes close. No rustling leaves, no distant traffic, no whisper of wind, nothing. Space is the universe's meditation room, and it stretches forever in free direction. So, get comfortable. Dim the lights. Let the wonder of the cosmos wash over you as we explore the calming truths hiding in the darkness above. If you're finding peace in these quiet facts about the cosmos, consider subscribing to Simple Science for Sleep. We explore the gentle wonders of science every night, creating a space for curious minds to rest. And we'd love to know where you're listening from tonight. Drop a comment telling us your location and what time it is there. It's beautiful, knowing we're all under the same stars, just in different moments. Picture this: you're floating in space. An explosion happens right next to you. A star tears itself apart. A meteor crashes into a distant moon, and you hear absolutely nothing. Not a whisper, not a rumble. Perfect silence. Because sound needs something to travel through. It needs air molecules bouncing into each other, carrying vibrations from source to ear. But space has no air, no molecules to bounce, no medium for sound to ride on. So even the most violent cosmic events unfold in complete, peaceful quiet. On Earth, we're never truly alone with silence. There's always something: the hum of electricity in the walls, the distant bark of a dog, our own heartbeat pulsing in our ears. But astronauts who've walked in space describe something different. A silence so deep it feels physical, like the universe itself is holding its breath. Chris Hadfield, who spent months aboard the International Space Station, said the silence of spacewalks was the most profound experience of his life. Not the view of Earth, not the weightlessness, the quiet. He said it felt like being wrapped in the softest blanket imaginable, except the blanket was nothingness itself. And here's what makes this beautiful. That silence isn't empty. It's full of patience, full of time moving at its own pace, full of stars burning through their fuel over billions of years, galaxies spinning through the void, planets orbiting in perfect mathematical rhythms. All of it happening without a single sound. The silence of space teaches us something important. Not everything needs noise to matter. The most significant things often happen quietly. Stars are born in silence. They live their entire lives without making a sound. They die the same way. Planets form from cosmic dust, slowly gathering themselves together over millions of years. And it all happens in perfect quiet. Think about that. The sun, that massive ball of fire 93 million miles away, is screaming with energy. Nuclear fusion in its core releases more power every second than humanity has used in all of history. But we hear none of it, because between us and the sun, there's only silence, only the peaceful void of space refusing to carry the sound. Even light, which travels from the sun to Earth in 8 minutes, makes the journey in complete quiet. Photons don't whisper as they cross the solar system. They simply arrive, gentle and silent, bringing warmth without announcing themselves. There's something deeply calming about knowing this exists. Above you, right now, past the blue sky and the clouds and the thin layer of air keeping you alive, there's a place where the universe simply is. No noise to distract from existence itself. No sound to interrupt the slow dance of celestial bodies. And you can visit this peace anytime you want. Just close your eyes and picture it. The endless dark, the patient stars, the quiet spinning of worlds. It's there, waiting, always has been, always will be. In that silence, stars are dying. Right now, this moment, but not the way you might think. We imagine stars going out in spectacular explosions. Hollywood loves showing us supernovas, those brilliant death throes lighting up galaxies. And yes, some stars do end that way, but most don't. Most stars die the way a candle dies, slowly, gently, fading into darkness over billions of years. Our sun will die like this. In about 5 billion years, it will simply run out of fuel. The hydrogen it's been fusing into helium will be gone, and when that happens, it won't explode. It will swell, slowly expanding into a red giant, its outer layers drifting away like dandelion seeds on a breeze. Then, it will shrink into a white dwarf, a small, dense ember of its former self. Still glowing, still warm, but quieter, smaller, peaceful. And then, over trillions of years, it will cool completely, becoming a black dwarf, a dark sphere floating through space, no longer giving light, no longer burning, just existing, a cosmic monument to a life well lived. This is how most stars end, not in violence, but in gradual surrender. They burn through their fuel at exactly the rate they need to. No rushing, no panic, just steady consumption over incomprehensible stretches of time. A star the size of our sun will live for 10 billion years. Larger stars live shorter lives, but even they take millions of years to burn out. Smaller stars, the red dwarfs, can live for trillions of years, longer than the current age of the universe. Right now, somewhere in the Milky Way, a star is entering its final years. Its light is dimming, its core is cooling, and it's doing so without fanfare. No alarm bells, no desperate final burst, just a slow fade into the cosmic night. There's something beautiful in this. The universe doesn't demand dramatic endings. It allows things to simply wind down, to rest, to become dark and quiet after billions of years of burning. Even the stars that do explode, the ones that become supernovas, don't do it suddenly. The explosion itself is quick, yes, but the process leading to it takes the star's entire lifetime. Millions or billions of years of steady burning, layer by layer, building up elements in its core. Iron, nickel, heavy metals that can't be fused any further. And when the core finally can't support itself anymore, when gravity wins, the collapse takes less than a second. But that second was earned over cosmic ages. And after a supernova, what's left? often a neutron star, a sphere 20 kilometers wide, spinning peacefully in space, or a black hole, quietly warping space around itself. Not monsters, not destroyers, just the natural next phase, the universe recycling itself. Every star that dies releases its contents back into space. The elements it created during its life scattered into the cosmic wind, and those elements become new stars, new planets, new chances for something beautiful to form. Death in space isn't an ending. It's a transformation, a change from one peaceful state to another. Stars don't fight it. They simply let it happen when their time comes. And in doing so, they contribute to something larger than themselves. Above you right now, ancient light is arriving from stars that may no longer exist. You're seeing their past, their long lives compressed into the photons reaching your eyes. And even though they might be gone, their light remains, still traveling, still gentle, still making the journey across the void. This is the rhythm of the cosmos. Slow, patient, peaceful. Nothing in space hurries toward its end. And those stars that died, they made you. Every atom in your body came from inside a star. Not metaphorically, not poetically. Literally, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it was forged in the nuclear furnace of ancient stars that burned out billions of years ago. You are stardust, and you're carrying the universe inside you at this very moment. Here's how it happened. When the universe began, there were only simple elements: hydrogen, helium, the lightest things possible. But stars are factories. They take those simple elements and, through the immense pressure and heat in their cores, they fuse them into heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. Nitrogen, neon. The process continues, building elements layer by layer, like a cosmic assembly line. But stars can only do this while they're alive. And when they die, especially the ones that explode as supernovas, they scatter all those newly made elements into space. They seed the universe with the building blocks of everything. Our solar system formed from one of those clouds, a nebula filled with the remnants of dead stars. As gravity pulled the cloud together, those elements clumped into the sun, the planets, and eventually into you. Every atom in your hand right now has traveled for billions of years to be exactly where it is. The iron in your blood was made inside a star at least 5 times larger than our sun. That star burned for millions of years, fusing lighter elements until it created iron in its core. And then it died. It exploded, and the iron scattered across space, drifting for billions of years until it became part of the cloud that formed Earth. Then it became part of the planet, then part of your food, then part of you. You are carrying that star's final gift. Every breath you take, every heartbeat, powered by atoms that once existed in the heart of a sun. The same is true for everything around you: the water you drink, the food you eat, the ground beneath your feet. All of it came from stars. The carbon that forms the base of all life on Earth was created inside stars that died before our sun was even born. We are made of ancient things, and here's the beautiful part. Those atoms don't stop with you. When you die, they'll return to the earth. They'll become part of the soil, the air, the water. They'll be taken up by plants, eaten by animals, breathed in by future humans. Your atoms will continue their journey. They might become part of a tree, a bird, a cloud, another person, living hundreds of years from now. You are not separate from the cosmos. You are the cosmos, a temporary arrangement of stardust that learned to think, to feel, to look up at the night sky and recognize itself. Carl Sagan said it best. We are a way for the universe to know itself. And he was right. The atoms in your brain, the ones firing right now as you process these words, were made in stars. The universe created those atoms. And now they're aware, they're conscious, they're looking back at the universe they came from. Your body is a collection of cosmic travelers, atoms that have existed for billions of years, witnessing the birth and death of stars, the formation of galaxies, the slow dance of the cosmos. And right now, they're here, with you, making you possible. So, when you look up at the stars, remember, you're not looking at something distant and separate. You're looking at family. You're looking at home. That same moon you're connected to, the one that's watched over Earth since life began, is leaving. Slowly, gently, at the speed your fingernails grow. Every year, the moon drifts about 3.8 centimeters farther from Earth. That's roughly 1.5 inches. You could measure it with a ruler if the distance wasn't already 238,000 miles. Scientists know this because astronauts left mirrors on the lunar surface during the Apollo missions. Researchers on Earth shoot lasers at those mirrors and measure how long the light takes to bounce back. And year after year, it takes a tiny bit longer. The moon is moving away. This has been happening since the moon formed 4.5 billion years ago. Back then, the moon was much closer, so close that it looked enormous in the sky, maybe 10 to 20 times larger than it appears now. The tides it created were massive, pulling ocean water hundreds of feet higher than today's tides. Days were shorter too, only 5 hours long, because Earth was spinning faster. But the moon's gravity tugged on Earth's oceans, and those tidal forces created friction. That friction slowed Earth's rotation, lengthening our days. And as Earth slowed, the moon gained energy, pushing it into a higher, wider orbit. This exchange has been happening for billions of years. Earth spinning slower, days getting longer, moon drifting farther. And it continues right now. This moment. While you're lying here, the moon is moving away from you. Not fast enough to notice. Not even fast enough to measure in a human lifetime without precise instruments. But it's moving, patient, steady, following the rules of physics that govern everything. In about 50 billion years, if Earth and the moon survive that long, the moon will be so far away that it will take 47 of our current days to orbit Earth once. And Earth will rotate so slowly that our days will match that rhythm, 47 days long. The moon will hang in the same spot in the sky, never rising or setting for anyone standing on one side of the planet. But 50 billion years is longer than the sun will live, so we'll never see that final state. The sun will expand into a red giant long before then, possibly swallowing both Earth and the Moon entirely. Our cosmic dance will end together. Still, for now, the Moon stays close enough to light up the night, close enough to pull the tides that helped life crawl from the oceans onto land, close enough to stabilize Earth's tilt, giving us consistent seasons instead of wild swings in climate. The Moon has been humanity's companion for every moment of our existence. It guided ancient travelers, inspired poets, marked the passage of time before we had calendars. Every human who has ever lived has looked up at the same moon you see tonight. Different positions in its orbit, yes, but the same scarred, patient face. And even as it drifts away, it's not abandoning us. It's just following the natural path set in motion billions of years ago. The same path everything in space follows. Slow, predictable, peaceful. Nothing in the universe rushes. Not the moon's retreat, not Earth's slowing spin, not the patient orbits of planets, or the gradual dimming of stars. Time moves differently out there, measured in ages, not seconds, in cosmic rhythms that unfold over billions of years. The moon will be here long after we're gone, still drifting, still patient, still lighting up someone's night, if anyone is left to see it. Light is patient too. Even though it's the fastest thing in the universe, it still takes time to arrive. The sunlight touching your skin right now left the sun 8 minutes ago. It's old. Light. Light that began its journey. Before you started reading this, before you settled into bed tonight, it traveled 93 million miles through empty space, moving at 186,000 miles per second, and it still needed 8 minutes to reach you. Which means if the sun suddenly vanished right now, you wouldn't know for 8 minutes. The sky would stay bright. The warmth would continue. Earth would keep orbiting around nothing, completely unaware that its star was gone. Then, 8 minutes later, the last light would arrive. And after that, darkness. The sun's absence would finally catch up to us. But the sun isn't going anywhere. It's been sending light on that 8-minute journey for 4.5 billion years. Every morning, every sunset, every moment of every day, light makes that trip. Reliable, steady, never late. And 8 minutes is nothing compared to starlight. When you look up at the night sky, you're seeing the past. Not metaphorically, literally. You're seeing light that left those stars years, decades, centuries, or millennia ago. The North Star, Polaris, is about 430 light-years away. The light you see from it tonight left that star in the year 1595, when Shakespeare was writing Romeo and Juliet. When the first English settlers were just beginning to think about sailing to America. That light has been traveling through space for over 4 centuries just to reach your eyes tonight. Betelgeuse, the red giant in Orion's shoulder, is roughly 550 light-years away. The light arriving from it now left during the Renaissance, before Newton discovered gravity, before telescopes existed. That ancient light crosses the universe while entire human civilizations rise and fall. And the farther you look, the deeper into the past you see. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. When you spot it on a clear night, you're seeing it as it was before humans existed, before Homo sapiens walked the Earth. Light from Andromeda has been traveling since our ancestors were barely standing upright. Some of the stars you see tonight no longer exist. They died centuries ago, thousands of years ago, but their light is still making the journey, still traveling through the void, still arriving at Earth right on schedule. You're watching ghosts, beautiful, luminous ghosts that show you what was, not what is. This is why astronomers say telescopes are time machines. The deeper they look into space, the farther back in time they see. The Hubble telescope has captured light from galaxies over 13 billion light-years away. Light that began its journey when the universe was young, when the first stars were just forming. That light has traveled longer than Earth has existed, longer than the sun has burned, just to be collected by a mirror orbiting our planet. Light doesn't hurry. Even at cosmic speed limits, it takes time to cross the vast distances between stars. And in that time, everything changes. Stars are born, stars die, planets form, life begins, civilizations rise, and the light just keeps traveling, carrying the image of what was. So when you look up tonight, remember, you're not seeing the universe as it is. You're seeing its history, a scattered timeline of moments, frozen in light, arriving at different speeds from different distances. The sky is a museum, and every star is an exhibit from a different era, and all that light arrives at exactly the right place. Earth sits in what scientists call the Goldilocks zone. Not too hot, not too cold, just right. This isn't luck, it's geometry. Earth orbits the sun at precisely the distance where water can exist as liquid. Any closer, and the oceans would boil away. Any farther, and they'd freeze solid. But here, 93 million miles from the sun, water flows. Life thrives. The temperature stays balanced. Venus is too close. Only 27 million miles closer than Earth, but that's enough. The sun's heat turned Venus into an oven. Surface temperatures reach 870 degrees Fahrenheit, hot enough to melt lead. Its atmosphere is thick carbon dioxide, trapping heat in a runaway greenhouse effect. Nothing lives there. Nothing could. Mars is too far, about 48 million miles farther from the sun than Earth. It gets less than half the sunlight we do. Its thin atmosphere can't hold heat. Temperatures swing wildly, from 70 degrees at the equator during summer days to minus 240 degrees at the poles during winter nights. Any water that once flowed on Mars is now locked in ice or lost to space. But Earth got it right. The zone where liquid water exists is narrow. In our solar system, it stretches from about 90 million miles to about 140 million miles from the sun. Earth sits comfortably in the middle of that range, not on the edge where things get risky. Right in the sweet spot. This matters more than you might think. Liquid water is essential for life as we know it. It's the medium where chemistry happens, where molecules meet and react, where the first simple cells formed billions of years ago. Without liquid water, Earth would be barren. Just another dead rock orbiting the Sun. And it's not just distance. Earth's size matters too. Big enough to hold an atmosphere, but not so big that the atmosphere becomes crushing like Jupiter's. Earth's gravity is strong enough to keep air molecules from drifting into space, but gentle enough to allow life to move and grow. Earth's magnetic field helps. Generated by the molten iron in our planet's core, it shields us from the sun's radiation. Solar wind, a constant stream of charged particles flowing from the sun, would strip away our atmosphere over time. But the magnetic field deflects it, protects us, keeps our air safe. Even Earth's tilt is perfect. 23.5 degrees. Enough to give us seasons, which create diverse environments and weather patterns, but not so extreme that half the planet becomes uninhabitable during winter. Some planets tilt so far they practically roll around the sun on their sides. Earth's tilt is moderate, balanced. All these factors, distance, size, magnetic field, tilt, work together. They create a stable environment, a place where temperature doesn't swing wildly, where water stays liquid, where an atmosphere can develop and persist, where life can begin and have time to evolve. Billions of planets exist in the universe. Most are too hot or too cold, too big or too small, orbiting too close to their star or too far away. But Earth landed in the perfect spot, the cosmic sweet spot where everything aligned. And that spot is home. The only place in the universe where we know for certain that life exists. A pale blue dot floating in the Goldilocks zone of an ordinary star, carrying oceans and forests and mountains and you. All of it possible because we're exactly where we need to be. If you could leave that perfect spot and float out into space, you'd experience something strange, something peaceful. You'd feel like you were falling forever. That's what weightlessness is. Not the absence of gravity, but the feeling of constant freefall. Astronauts in the International Space Station aren't floating because there's no gravity up there. Earth's gravity at that altitude is still about 90% as strong as it is on the ground. They float because they're falling toward Earth at exactly the same speed the station is moving forward. They're in orbit, constantly falling but never landing, and it feels incredible. Every astronaut who's experienced it describes weightlessness as the most peaceful sensation they've ever known. No pressure on your joints, no weight on your spine. Your body completely relaxed in a way it never can be on Earth. Even lying in the most comfortable bed, gravity still pulls on you, still compresses your skeleton, still makes your heart work to pump blood upward. In space, all that vanishes. Your heart doesn't have to fight gravity. Blood flows evenly throughout your body. Your spine stretches out, which is why astronauts grow about 2 inches taller in orbit. Not permanently, they shrink back down when they return, but for those months in space, they're literally taller because nothing is compressing them. Astronaut Chris Hadfield said, "Floating felt like being cradled by the universe. No tension, no strain, just existence without effort. You don't have to hold yourself up. You don't have to maintain posture. You simply are. Present, weightless, free. There's no up or down in orbit. The space station has labels on the walls saying floor and ceiling, but they're arbitrary. Astronauts sleep in any orientation. They work sideways. They flip and tumble through modules like swimmers in an invisible ocean. And after a few days, their brains stop, trying to assign up and down. They adapt, accept that direction has no meaning anymore. This creates moments of profound stillness. You can push off a wall and glide across the entire station without moving a muscle. Your body drifts in a straight line, following Newton's first law. An object in motion stays in motion, and you are that object, peacefully coasting through space until something stops you. Scott Kelly, who spent a year aboard the ISS, talked about floating to a window and just hovering there for hours. Watching Earth spin below, completely still, no fidgeting, no need to adjust his position, just floating and observing. He said it was the closest he's ever come to meditation, the external stillness matching his internal state. Even sleep is different in weightlessness. You can sleep floating in the middle of a room, arms drifting wherever they want, legs relaxed, head unsupported. Your body finds its natural position without gravity dictating the rules. Some astronauts strap themselves into sleeping bags attached to walls just to feel anchored. Others let themselves float free, trusting the station's gentle air currents to keep them from drifting into equipment. And when they return to Earth, astronauts say gravity feels harsh, oppressive. They drop things constantly because their brains forgot weight exists. They stumble because walking requires effort again. Their bodies ache from supporting themselves. Some describe it as being betrayed by their own planet. Earth suddenly feels heavy, demanding. After months of peaceful floating, standing upright becomes work. Weightlessness is the universe's gift, a reminder that the forces we take for granted aren't everywhere, that peaceful existence without strain is possible, that floating through the cosmos is the natural state of things. Out there in that floating darkness, black holes exist, and they're nothing like the monsters movies make them out to be. Black holes don't chase, they don't hunt, they don't reach out with tentacles of gravity and pull things in. They just sit there, spinning quietly, warping space around them, waiting for something to drift too close. Most black holes are alone, floating in the empty spaces between stars, too far from anything to affect it. They're not sucking up the universe. They're not growing uncontrollably. They're just existing, patient, still. Following the same laws of physics, everything else follows. If you could replace the sun with a black hole of the same mass, nothing would change for Earth. We'd lose light and heat, yes, and we'd die from cold and darkness. But our orbit would stay the same. The black hole's gravity would be identical to the sun's gravity, because mass is what matters, not what form it takes. Earth would continue circling that black hole exactly as it circles the sun now. No spiral into oblivion, no dramatic consumption, just the same quiet orbit we've maintained for billions of years. Black holes only affect things that come very close. There's a boundary called the event horizon. Cross that line and you can't escape. But that line isn't expanding. It's not reaching out. It's just there, fixed. and for most black holes, it's small. A black hole with the mass of our Sun would have an event horizon only 3 miles across. Tiny, considering the scale of space. Even approaching a black hole would be slow. You'd have to travel for years, maybe centuries, depending on where you started. And as you got closer, you'd notice strange things. Time would behave differently. Light from stars behind the black hole would bend around it, creating distorted images. Space itself would curve in ways that don't make intuitive sense. But nothing would feel violent. You'd just be drifting closer, pulled by gravity the same way Earth is pulled by the Sun. Gentle acceleration. The black hole wouldn't suddenly grab you. It would just keep pulling. Steady, inevitable, patient. Scientists think most galaxies have a supermassive black hole at their center. The Milky Way has one. It's called Sagittarius, a star. 4 million times the mass of our Sun, sitting at the heart of our galaxy, 26,000 light-years from Earth. And we're perfectly safe from it. It's too far away. Its gravity doesn't reach us any differently than any other massive object that far away would. Sagittarius, a star, just sits there. Occasionally, a star or cloud of gas drifts too close and gets consumed. The black hole pulls it apart, heats it up as it spirals inward, and eventually it crosses the event horizon and disappears. But this happens slowly, over months or years, not in a sudden violent snap. Most of the time, black holes do nothing. They spin in the dark. Some spin incredibly fast, rotating hundreds of times per second. Others barely spin at all. But fast or slow, they're just objects. Spheres of curved spacetime, not conscious, not malicious, not dangerous, unless you go looking for danger. They're the universe's recycling bins, taking matter and energy that crosses their event horizon and locking it away from the rest of the universe. Nothing comes back out, but nothing was going to anyway. The matter that falls into a black hole was already on that path, already doomed. The black hole just completes the journey. Beyond those black holes, beyond all the stars and galaxies we can see, the universe has an edge, not a wall, not a boundary you could touch, but a horizon, a point past which we simply cannot see. It's called the observable universe, and it ends about 46 billion light-years away in every direction. Not because the universe stops there, it doesn't. Space keeps going, probably forever. But that's as far as light has had time to reach us since the beginning of everything. The universe is 13.8 billion years old. You'd think that means we could see 13.8 billion light-years in any direction. But the universe has been expanding this whole time. So light that left distant galaxies billions of years ago has been traveling through stretching space. By the time it reaches us, those galaxies are much farther away than they were when the light started its journey. That's why the edge of the observable universe is 46 billion light-years away, not 13.8. The space itself expanded while the light was traveling, and that edge is moving farther away every moment. As time passes, light from more distant regions reaches us. Our view grows wider. The observable universe expands. But there will always be an edge, always a horizon we cannot see past, because light travels at a fixed speed, and the universe has a finite age. There simply hasn't been enough time for light from truly distant places to reach us yet. And here's the peaceful part. Beyond that edge, the universe continues. Galaxies we'll never see, stars that will burn and die without ever appearing in our sky. Planets where, perhaps, other beings look up at their own night sky and wonder what lies beyond their horizon. We are not at the center of the universe. The observable universe is centered on us only because we're observing from here. Someone in a galaxy 10 billion light-years away would see a different observable universe. Their edge would include galaxies we can't see. And our edge would include galaxies invisible to them. Everyone gets their own horizon. This means the universe is larger than what any single observer can see. Maybe infinitely larger. And that's okay. We don't need to see everything to understand our place in it. We can be content with our corner, our bubble of visibility. The edge of the observable universe isn't dark. It's filled with the cosmic microwave background radiation, the afterglow of the Big Bang, the oldest light in existence, stretched by expansion into microwaves. It comes from every direction, a faint hum that fills all of space. That radiation marks the moment when the universe became transparent, about 380,000 years after the Big Bang. Before that, the universe was so hot and dense that light couldn't travel. It would bounce off particles constantly. But when things cooled enough, light broke free. And it's been traveling ever since. That ancient light forms our horizon. We cannot see past it, because before it was released, the universe was opaque. So, the edge of the observable universe isn't arbitrary. It's the farthest back we can look, the earliest moment we can witness. And beyond it, space continues, silent, patient, filled with things we'll never know about, galaxies forming and dying without an audience, stars burning in permanent isolation from our view, the universe doing what it does, unconcerned with whether anyone sees it. There's something calming in that. The universe is bigger than our ability to observe it, and it doesn't need our attention to exist. Within that vast space, galaxies move like dancers, slow, graceful, following rhythms that take millions of years to complete. Our galaxy, the Milky Way, is moving toward the Andromeda Galaxy at about 70 miles per second. That sounds fast, but the distance between them is so vast that they won't collide for another 4 billion years. 4 billion. That's almost as long as Earth has existed. The collision has been scheduled since long before our planet formed, and it's still billions of years away. When they finally do meet, it won't be violent, not the way you'd imagine. Galaxies are mostly empty space. The distance between stars is enormous compared to the size of the stars themselves. So when two galaxies merge, their stars don't crash into each other. They pass by, weaving through each other like two swarms of fireflies drifting together. Some stars will get flung out into deep space. Some will settle into new orbits. The supermassive black holes at each galaxy's center will eventually spiral together and merge. But for the stars themselves, for planets, for anything orbiting those stars, the collision will be gentle. A slow rearrangement taking millions of years. Our sun will probably survive. it might get thrown into a different part of the new combined galaxy. Earth might see a completely different night sky, but the violence we associate with collisions won't apply. Space is too big. Things are too far apart. There's room for everything to coexist. And this happens everywhere. Galaxies collide constantly across the universe. We can see it through telescopes. Spiral galaxies merging into elliptical ones. Small galaxies being absorbed by larger ones. Streams of stars stretching between two galaxies as gravity pulls them together. The Milky Way itself is currently consuming smaller galaxies. Right now, dwarf galaxies that ventured too close are being torn apart by our galaxy's gravity. Their stars are joining ours. Their gas clouds are becoming part of our spiral arms. It's been happening for billions of years and will continue for billions more. But it happens slowly. Stars from those dwarf galaxies take millions of years to settle into their new orbits. There's no sudden impact, no dramatic moment when everything changes. Just gradual incorporation, one slow orbit at a time. Even the shapes of galaxies reflect this peaceful movement. Spiral galaxies have their arms because of rotation. As the galaxy spins, slower on the outside than the inside, stars and gas form patterns. Like cream stirred into coffee. The arms aren't solid structures, they're density waves, regions where stars bunch up temporarily as they orbit. The stars themselves move through the arms, spending time in them and then leaving. But the pattern persists. Elliptical galaxies are smooth and round because they've been through collisions before. Their stars orbit in random directions. No organized rotation, no spiral pattern. Just a cloud of stars moving in their own paths, held together by gravity. They look calm because they are calm. No new star formation, no dramatic structure, just old stars orbiting peacefully. The universe is full of this slow motion. Galaxies orbiting each other. Star clusters drifting through galaxies. Individual stars moving through space at speeds that seem fast to us, but are glacial on cosmic scales. Everything following gravity's patient pull. Everything dancing to music that plays over billions of years. And somehow, in all that motion, there's order, patterns, rhythms. The universe doesn't move randomly. It moves like choreography. Slow choreography that takes longer than civilizations to complete. Underneath all that motion, the universe hums. A faint glow fills every corner of space. The afterglow of creation itself. It's called the cosmic microwave background radiation. And it's everywhere. In this room, between the stars, in the deepest voids of space. A remnant of the moment when the universe became transparent. When light could finally travel freely through space without being absorbed. That happened 380,000 years after the Big Bang. Before that, the universe was too hot, too dense. Free electrons scattered photons constantly. Light couldn't move more than a tiny distance before bouncing off something. The universe was opaque, a fog of energy and matter. But as the universe expanded, it cooled. Eventually, it cooled enough for electrons to bond with protons, forming the first atoms, mostly hydrogen. And when that happened, light was free. It could travel, and it's been traveling ever since. That light has been stretched by the expansion of the universe. What started as visible light, even ultraviolet, has been pulled into longer wavelengths. Now it's microwaves, too low in energy for our eyes to see, but it's there, washing over everything, a constant, gentle bath of ancient radiation. If you could see microwaves, the entire sky would glow, not with stars or galaxies, just a faint, even glow coming from every direction. The temperature of that glow is 2.7 degrees above absolute zero. Cold, but not quite the coldest possible. That tiny bit of warmth is the universe's memory of being hot. Scientists discovered this radiation by accident in 1964. Two researchers at Bell Labs were testing a radio antenna and kept picking up noise they couldn't explain. Static that came from everywhere. They cleaned the antenna, removed bird droppings, checked every piece of equipment. The noise remained. It wasn't noise. It was the universe itself, the oldest light in existence, filling space with a whisper. And that whisper tells us about the beginning, about the shape of the universe, about how matter was distributed in those early moments. The cosmic microwave background isn't perfectly uniform. It has tiny variations, spots that are slightly warmer or slightly cooler, only by millionths of a degree. But those tiny differences mattered. They were the seeds that grew into galaxies. Regions where matter was slightly denser pulled in more matter through gravity. Over billions of years, those small fluctuations became stars, galaxies, clusters of galaxies. Everything we see today started as tiny ripples in that ancient light. Maps of the cosmic microwave background look like mottled patterns, splotches of color representing temperature variations so small they barely exist. But astronomers study those maps intensely because they're baby pictures of the universe, snapshots of what existed before stars, before galaxies, before anything complex. And that light is still arriving. Right now. Photons that have been traveling for 13.8 billion years are reaching Earth for the first time. Hitting your skin, passing through your body. Ancient light that witnessed the birth of the universe, finally completing its journey. You're bathed in creation's afterglow, the universe's first light, stretched and cooled, surrounds you constantly. It's been traveling since before matter existed in any form we'd recognize. Before atoms, before chemistry, before anything resembled anything. And it will keep traveling forever. As the universe expands, that light will stretch further, cool more, become fainter, but it will never disappear. The cosmic microwave background is permanent, a record that cannot be erased. The universe's way of remembering where it came from. That same order exists closer to home. Planets orbit like clockwork, precise, predictable, never late. Earth completes one orbit around the Sun in 365.25 days, every year, without variation. Mercury takes 88 days, Mars takes 687, Jupiter needs 12 years, Saturn needs 29. Each planet follows its path with mechanical precision. This isn't coincidence. It's gravity and momentum working together. When the solar system formed 4.5 billion years ago, planets settled into stable orbits. Orbits where the pull inward from the Sun's gravity exactly balances the planet's momentum, carrying it forward. That balance hasn't changed, won't change. The math doesn't allow for it. You could set your watch by planetary motion if watches lasted long enough. Venus passes between Earth and the Sun in a predictable pattern. Every 105 years, it happens twice in 8 years. Then, not again for another 97 or 105 years. We can calculate these transits centuries in advance. We can look back through history and confirm they happened exactly when the math says they should have. Ancient astronomers noticed this. They didn't understand gravity or orbital mechanics, but they saw the pattern. Planets wandered across the sky in predictable ways. You could track their positions, predict where they'd be months or years later. The word planet comes from the Greek word for wanderer, but it's a wandering that follows rules. This reliability extends beyond our solar system. Exoplanets, planets orbiting other stars, follow the same laws. We discover them by watching stars wobble slightly as planets orbit, or by measuring the tiny dimming when a planet passes in front of its star from our perspective. Those wobbles and dimmings happen on schedule, regular as heartbeats. Some exoplanets have extreme orbits, hot Jupiters that circle their stars in just a few days. Planets so close to their suns that their surfaces are molten. But even those extreme orbits are stable. The planet isn't spiraling inward or being flung outward. It's exactly where it needs to be to maintain that orbit. Kepler's laws describe all of this. 3 simple mathematical relationships discovered 400 years ago. They work for every planet in every solar system. The shape of the orbit, the speed at different points, the relationship between orbital period and distance from the star. All of it predictable, all of it reliable. This means we can plan. Space missions to Mars launch during specific windows, when Earth and Mars are positioned favorably. Those windows open every 26 months like clockwork. Miss the window, wait 2 years for the next one. But it will come. The planets will align again, because they always do. Voyager 2 used this reliability to visit multiple planets. Launched in 1977 during a rare alignment when Jupiter, Saturn, Uranus, and Neptune were positioned so a spacecraft could use each planet's gravity to reach the next. That alignment happens once every 176 years. Predictable, knowable decades in advance. The solar system is a clock, not the kind you wear on your wrist, the kind that takes years or centuries to complete one cycle. But it's a clock nonetheless. Every planet a hand moving at its own speed. All of them synchronized by gravity's pull. All of them exactly on time. And it's been this way since the beginning. 4.5 billion years of perfect timekeeping. No delays, no drift. Just planets following the paths physics laid out for them, moving through space with infinite patience. And those planets aren't alone. Most have moons, companions orbiting beside them. The universe doesn't like solitude. Earth has 1 moon. Mars has 2. Jupiter has 95 confirmed moons. Saturn has 146. And those numbers keep growing as we discover smaller and smaller objects orbiting these giant planets. The solar system is full of moons. Some are massive. Ganymede, Jupiter's largest moon, is bigger than Mercury. Titan, Saturn's largest, has a thick atmosphere and lakes of liquid methane. These aren't just rocks floating in space. They're worlds, complex, diverse, each with its own story. Others are tiny, just a few miles across, irregular chunks of rock and ice captured by a planet's gravity. They orbit far from their host planets in strange, elongated paths, but they orbit nonetheless, held in place by the same forces that keep our moon circling Earth. Europa, one of Jupiter's moons, has an ocean beneath its icy surface. More water than all of Earth's oceans combined. Covered by a thick shell of ice, that ocean stays liquid because of tidal heating. Jupiter's gravity squeezes Europa as it orbits, creating friction, generating heat. Enough heat to keep water liquid despite being far from the sun. Scientists think life could exist in that ocean. Not life like us. Something simpler. Microbes clustered around hydrothermal vents on the ocean floor. The same kind of vents that support life in Earth's deepest oceans. We haven't looked yet, haven't sent a probe there, but it's possible. Life might exist on a moon, not a planet. Enceladus, one of Saturn's moons, has geysers. Jets of water vapor shooting hundreds of miles into space from cracks in its icy surface. That water comes from an underground ocean. Cassini, the spacecraft that orbited Saturn for 13 years, flew through those geysers, tasted the water, found organic molecules, the building blocks of life. Even our moon is special. It's unusually large compared to Earth. Most planets have tiny moons or no moons at all, but our moon is about a quarter the size of Earth. We think it formed when another planet-sized object crashed into early Earth. The collision threw debris into orbit, and that debris clumped together into the moon. That impact could have destroyed Earth, but instead, it gave us a companion, a stabilizer. The moon's gravity keeps Earth's tilt steady. Without it, our axis would wobble wildly. Seasons would be chaotic. Climate would swing between extremes. Life might not have had the stable environment it needed to evolve. So we owe our existence to our moon. And our moon exists because of a cosmic accident 4.5 billion years ago. A collision that could have ended everything, instead created the conditions for everything. Looking beyond our solar system, we're finding moons around exoplanets too. We can't see them directly. They're too small, too faint, but we can detect their effects. The way they tug on their host planets, the way they alter the light curve when planet and moon pass in front of their star together. The universe makes companions. It takes matter and arranges it into systems. Stars with planets, planets with moons. Even asteroids have tiny moons. Things orbit other things. Nothing drifts alone if gravity has anything to say about it. We're part of that pattern, Earth and its moon. Two bodies locked in a slow dance, and we're surrounded by countless other pairs doing the same thing. Moons and planets, partners in the cosmic ballet. And all those moons orbit planets that orbit a star. Our star, the sun. And here's the humbling part. It's completely ordinary. The Sun isn't special. It's not the biggest star, not the brightest, not the hottest or the coolest. It's medium, a middle-aged yellow dwarf star, one of hundreds of billions in the Milky Way galaxy alone. If you lined up all the stars in the universe by size, brightness, and temperature, the Sun would sit right in the middle of the pack. It's about 4.5 billion years old, halfway through its life. In another 5 billion years, it will swell into a red giant, then shrink into a white dwarf, then cool into a black dwarf. The same fate awaiting billions of other medium-sized stars. Nothing unique about the process. There are stars hundreds of times larger than the Sun. Betelgeuse, if placed at the center of our solar system, would swallow Mercury, Venus, Earth, and Mars. Its surface would reach past the asteroid belt. Scuti, one of the largest known stars, is 1,700 times wider than the Sun. If the Sun were a marble, Scuti would be a sphere 10 feet across. And there are stars much smaller, red dwarfs that are only 10% the Sun's mass. They burn so slowly they'll live for trillions of years, far longer than the current age of the universe. Some red dwarfs formed shortly after the Big Bang and will still be burning long after every other type of star has died out. But here's what makes ordinariness beautiful. Being average means we're part of the pattern. The Sun isn't an exception. It's an example. And that means everything we observe about the Sun, about our solar system, about the conditions that led to life on Earth, could be happening elsewhere, around other ordinary stars, in other unremarkable solar systems. The Sun produces energy the same way every star does. Nuclear fusion. In its core, hydrogen atoms slam together under immense pressure and temperature. They fuse into helium, and in that process, they release energy. Light, heat, the warmth you feel on your skin, the light that feeds plants. All of it from fusion happening 93 million miles away. This has been happening for 4.5 billion years. The Sun converts about 600 million tons of hydrogen into helium every second. And it has enough hydrogen left to continue for another 5 billion years. Steady, reliable, ordinary. Ancient humans thought the Sun was a god, unique, powerful, demanding worship. And in a sense, they were right to revere it. Without the Sun, Earth would be a frozen rock. No warmth, no light, no life. The Sun is essential to our existence. But it's not unique. There are stars just like it scattered throughout every galaxy. Yellow dwarfs burning hydrogen, producing light, possibly supporting planets where life asks the same questions we ask, where beings look up at their ordinary star and wonder if they're alone. We're not at the center of anything. Not the solar system, that's the Sun. Not the galaxy, not the universe. We orbit an average star in an average position in an average galaxy floating through space with billions of other average galaxies. And somehow, that's comforting. We don't need to be exceptional to matter. We don't need to be the center of everything to have value. We're part of the cosmic ordinary. And the cosmic ordinary is vast and beautiful and full of possibility. Being normal means we belong here. That ordinary space around our ordinary star has something surprising. It smells. Not the vacuum itself, but the things floating in it. Astronauts who've done spacewalks describe a distinct odor that clings to their suits when they return to the airlock. They say space smells like seared steak, burnt metal, gunpowder, hot electronics, a sharp, acrid scent that's unmistakable once you've experienced it. The smell comes from dying stars, specifically from polycyclic aromatic hydrocarbons, complex molecules released when stars burn. They drift through space as cosmic dust. And when astronauts are outside the station, those molecules stick to their suits, the fabric, the metal. When they bring their suits back into the pressurized environment and remove their helmets, those molecules interact with moisture in the air. And they smell. It's the scent of the universe's chemistry. Carbon-based molecules formed in stellar furnaces, the same building blocks that eventually became life on Earth. Astronauts are literally smelling stardust. But that's not the only smell in space. The center of the Milky Way smells different. Scientists analyzing radio signals from Sagittarius B2, a massive cloud of gas near the galactic core, found ethyl formate, the same chemical that gives raspberries their smell, and rum its taste. There's enough ethyl formate in that cloud to make billions of bottles of rum, more than humanity could drink in 1,000,000 years. It's floating out there right now, a cosmic cocktail nobody can taste, mixed with other organic molecules, amino acids, sugars, the chemical precursors to life. These smells tell us something important. Space isn't empty. It's full of chemistry, molecules bumping into each other, bonding, breaking apart, creating more complex structures. The same processes that happen in laboratories happen naturally in space, just slower, spread across light years instead of test tubes. Even planetary atmospheres have smells. Venus would smell like rotten eggs. Its atmosphere is thick with sulfur dioxide. Mars probably smells like rust. Iron oxide dust covers its surface. Titan, Saturn's largest moon, might smell like gasoline. Its atmosphere is full of methane and ethane, hydrocarbons similar to what we pump into cars. We can't smell these things directly. Spacesuits filter air. Spacecraft are sealed, but we know the chemistry. We can detect the molecules, and we know how those molecules interact with human senses based on Earth chemistry. This makes space feel more real. Not just an abstract void, but a place with sensory qualities, where things have textures and temperatures, and yes, smells. A place you could experience if you had the right equipment. It grounds the cosmic in the familiar. Burnt steak, raspberries. These are everyday smells, things you can picture. And knowing they exist in space makes the universe feel less alien, more relatable. The same chemistry that creates flavors and scents on Earth exists out there, just in different combinations, different concentrations. Scientists studying comets found they contain alcohol and sugar, real ethanol and glycolaldehyde, the building blocks of alcoholic drinks and simple sugars. Comets are essentially dirty snowballs flying through space, carrying the ingredients for a very strange cocktail. None of this means space is habitable. You still can't breathe there. You'd still freeze or boil, depending on where you were. Pressure, or lack of it, would kill you. But space isn't the sterile void we once imagined. It's chemically rich, full of the same elements and compounds that make Earth interesting, just arranged differently, floating freely instead of being bound to a planet's surface. One of the most beautiful things in space is temporary. Saturn's rings, those stunning bands of ice and rock circling the planet. They won't last forever. Saturn's rings are disappearing. Right now, this moment, they're raining down onto the planet. Ice particles spiral inward, pulled by Saturn's gravity and magnetic field. Scientists call it ring rain, and it's happening at a rate of about 2,000 pounds per second. That sounds like a lot, but Saturn's rings contain trillions of tons of material, so they're not vanishing overnight. Current estimates suggest they'll be gone in about 300 million years, maybe less, maybe a bit more. But on cosmic timescales, that's soon. 300 million years ago, dinosaurs were just beginning to appear on Earth. In another 300 million years, there'll be ancient history, and Saturn will be ringless. A smooth gas giant, still beautiful, still massive, but missing its most iconic feature. The rings are young. We think they formed only a few 100 million years ago. A moon or comet wandered too close to Saturn and got torn apart by tidal forces. The debris spread into a flat disk around the planet's equator. Gravity and orbital mechanics kept it organized into distinct rings with gaps between them. But that organization is fragile. Saturn's gravity constantly pulls at the ring particles. Some spiral inward and fall into the planet's atmosphere. Others get knocked outward by collisions with each other. The rings are slowly dissipating, spreading out, losing material. This means we're lucky. Lucky to exist during the brief window when Saturn has rings. If intelligent life had evolved on Earth 1 billion years earlier, they would have looked up and seen a ringless Saturn. If we'd evolved 1 billion years later, same thing. We happen to be here during the few 100 million years when Saturn looks like this. And Saturn isn't the only planet with rings. Jupiter has faint rings. Uranus has rings. Neptune has rings. They're all temporary, all slowly decaying, all destined to disappear eventually. Jupiter's rings are constantly replenished by dust kicked up from its moons when meteorites hit them. Without that steady supply, Jupiter's rings would vanish quickly. They're thinner and darker than Saturn's, barely visible unless you know where to look, more like a faint haze than solid bands. Uranus and Neptune have narrow rings, dark rings made of material so black they barely reflect any light. We didn't discover them until spacecraft flew past those planets in the 1980s. They're there, orbiting silently, fading slowly like Saturn's. Even the gaps in Saturn's rings are temporary. The Cassini division, the largest gap, exists because of gravitational resonance with one of Saturn's moons, Mimas. Its orbit creates a pattern that clears particles from that region. But orbits change over time, slowly, imperceptibly. Eventually, that resonance will shift, and the gap might fill in or move. Nothing in space is permanent, not even the structures that seem eternal. Mountains on Earth erode, continents drift, species go extinct, and Saturn's rings rain down onto the planet that created them. But here's the peaceful part. We don't need them to last forever to appreciate them. Their beauty exists right now, today, this moment, and that's enough. We get to witness something temporary, something rare, something that won't always be there. And there's a gift in that, a reminder that even the grandest features of the universe have their time and then gracefully fade away. Saturn's rings contain billions of pieces, but that's nothing compared to the number of stars in the universe. There are more stars than grains of sand on all of Earth's beaches. Every beach, every coast, every shoreline on the entire planet. Count every grain of sand and you still wouldn't reach the number of stars. Scientists estimate about 100 billion trillion stars exist in the observable universe. That's a 1 followed by 23 zeros. Written out, it looks like this: 100,000 billion billion. The number is so large, it stops meaning anything. Your brain can't picture it. Nobody's can. To put it another way, there are roughly 10,000 stars for every grain of sand on Earth. 10,000. If you held a single grain of sand in your hand, somewhere in the universe, 10,000 stars are burning. And you're holding just one grain. The Milky Way alone contains between 100 and 400 billion stars. Our galaxy, just one of hundreds of billions of galaxies. And each of those galaxies contains billions or trillions of stars. The scale becomes incomprehensible quickly. If you tried to count the stars in the observable universe, counting 1 per second without stopping, it would take you 3 trillion years. That's 200 times longer than the current age of the universe. You'd need to start counting before the Big Bang happened and continue long after the last star burns out. And you still wouldn't finish. Most of those stars have never been seen by human eyes, never been studied, never been named. They're just out there, burning, following the same physics our sun follows, creating light that will never reach Earth because they're too far away or too dim. Some of those stars have planets. We don't know how many, but the more we look, the more planets we find. It seems like most stars have planets, which means there could be trillions and trillions of planets out there. Rocky planets, gas giants, ice worlds, every type imaginable. And some of those planets are in the right zone, the Goldilocks zone where liquid water can exist, where life might develop. We don't know if life exists on any of them, but the numbers suggest it's likely. With trillions of planets, odds are some of them host life, maybe even intelligent life, looking up at their sky and wondering the same things we wonder. This vastness could feel lonely, could make us feel insignificant. A tiny speck on a small planet orbiting an ordinary star in an unremarkable galaxy. And in a sense, that's true. We are small, cosmically small, infinitesimally small. But here's the other way to look at it. We're part of something unimaginably huge. We're connected to all those stars, made from the same elements, following the same laws, participating in the same cosmic story. Our atoms came from stars. We'll return to space eventually. We'll become part of new stars, new planets, new possibilities. You are small, but you're also part of everything. Every atom in your body has a connection to the wider universe, to all those stars, to all that space. You're not separate from it. You're woven into it. And when you look up at the night sky and see a few thousand stars, remember, those are just the closest ones, just the brightest, just the ones whose light happens to reach your exact location on Earth. Behind them, invisible to your eyes, are billions and billions more, all burning quietly, all adding their light to the universe, all part of the same infinite family you belong to. And humanity has reached out into that vastness, sent a messenger, a tiny spacecraft carrying our voice into the infinite dark. Voyager 1, launched in 1977, still traveling, still sending signals back to Earth. The farthest human-made object in existence, about 15 billion miles from home, so far away that light from the sun takes 22 hours to reach it. Every day, Voyager 1 sends a signal, a faint radio whisper, 20 watts of power, less than a refrigerator light bulb. By the time that signal reaches Earth, it's spread across space so thin it arrives weaker than a snowflake falling on your hand. But we can hear it, giant radio dishes pointed at that spot in the sky, listening for Voyager's voice. The signal takes 22 hours to arrive, so when scientists send a command to Voyager, telling it to do something, they wait. 22 hours for the command to reach the spacecraft. Then, 22 hours for Voyager's response to come back. 44 hours total, nearly 2 days for a single conversation. The ultimate long-distance relationship. Voyager isn't coming back. It's leaving the solar system, already past the heliopause, the boundary where the sun's influence fades and interstellar space begins. It's in the space between stars now, the true void, and it's still moving. 38,000 miles per hour. Fast by human standards. Glacial by cosmic ones. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. Not close enough to be captured, not close enough to crash, just a flyby. A brief visit before continuing into deeper space. And humans probably won't be listening anymore by then. Voyager's power will have run out long before, its transmitter silent. The spacecraft carries a golden record, a disc with sounds and images from Earth, music, greetings in 55 languages, pictures of people, animals, landscapes, instructions for how to play it, just in case someone finds it. The odds of that happening are impossibly small. Space is vast and Voyager is tiny. But the gesture matters. We sent a message saying we were here. We existed. We looked up at the stars and wanted to be part of them. Voyager's power comes from plutonium, radioactive decay generating electricity. But plutonium doesn't last forever. Scientists estimate Voyager's systems will shut down around 2025, maybe 2030 if they're lucky. After that, it will go silent, still traveling, still moving through space, but no longer calling home. When that happens, Voyager will become a time capsule, a fossil from human civilization, drifting through the galaxy for billions of years, long after Earth is gone, long after the sun expands and dies. Voyager will still be out there, a tiny monument to a species that once looked up and wondered. But for now, we can still hear it, every day, a faint signal from the edge of everything we know, proof that we can reach beyond ourselves, that we can send something into the cosmos, and it keeps going, keeps functioning, keeps whispering back that it's still there, still okay, still carrying our message into the dark. It's been traveling for 47 years, longer than most humans live, and it's still only just begun its journey. The galaxy is so large that Voyager could travel for millions of years and never reach the other side. Space doesn't end, and neither does Voyager's path through it. Voyager is heading into a universe that's getting darker, slowly, inevitably. And that's okay. The universe is expanding, not just growing, accelerating. Galaxies are moving away from each other faster and faster. The space between them stretches, and as it stretches, the universe becomes less dense, more spread out, cooler, darker. Eventually, trillions of years from now, galaxies will be so far apart that light from one will never reach another. Each galaxy will be alone in its own bubble of darkness, surrounded by nothing but the stretched thin cosmic microwave background. Beings living in those distant galaxies will look up and see only their own stars. No neighboring galaxies, no deep space, just their home and darkness. Then, over even longer timescales, stars will stop forming. All the hydrogen and helium, the fuel for star creation, will be used up or locked in objects that can't collapse to make new stars. The last stars will be the longest-lived ones, tiny red dwarfs burning slowly for trillions of years. And eventually, even they'll run out of fuel. When the last star dies, the universe will enter what scientists call the degenerate era. No more starlight, just the faint glow of cooling white dwarfs, neutron stars, and black holes. Objects that once were stars, now just remnants, slowly releasing their remaining heat into the void. After that comes the black hole era. The only significant objects remaining will be black holes. Everything else, planets, dead stars, loose matter, will have either fallen into black holes or been flung out into the expanding emptiness. And those black holes will evaporate, slowly, through a process called Hawking radiation. Even the largest black holes will eventually lose all their mass and disappear. This takes an unimaginable amount of time. A Google years. That's 10 to the power of 100. A 1 followed by 100 zeros. Longer than our minds can process. Longer than comparisons can capture. But it will happen. Physics says so. And then the universe reaches its final state. The heat death, maximum entropy. Everything spread perfectly evenly across infinite space. No stars, no black holes, no structure, just particles, spread so far apart they might as well not exist. Photons stretch to wavelengths longer than the observable universe, a temperature barely above absolute zero. Darkness, silence, peace. This isn't a tragedy. It's just the natural end. The universe began with incredible energy concentrated in a tiny point. It's been spreading that energy out ever since. Entropy always increases. Order becomes disorder. Hot becomes cold. Concentrated becomes diffuse. The universe is following the rules it set at the beginning. And in a way, it's peaceful. No more explosions, no more collisions, no more violence. Just infinite calm. The ultimate rest after trillions upon trillions of years of activity. The universe will have told its story, played out every possibility, and then it will sleep. We won't be here to see it. Nothing will. Life requires energy differences, hot and cold, light and dark, something to power metabolism. When everything is the same temperature, when energy is spread perfectly, even, life becomes impossible. The universe's final state is sterile, empty, but also perfectly balanced. It's so far in the future, it doesn't affect us. The sun has 5 billion years left. Humanity could last millions or billions of years if we survive. That's enough time for everything that matters to us. Enough time for countless generations to look up at a sky full of stars and feel wonder. But that's not tonight. Tonight, you're here, under the same stars that have watched over Earth for billions of years. The same stars the dinosaurs saw. The same stars ancient humans used to navigate. The same stars that witnessed the rise and fall of civilizations, the birth of language, the first time someone looked up and wondered what those lights were. You're lying under that sky right now. The stars haven't changed. Polaris still points north. Orion still hunts across the winter sky. The Big Dipper still wheels around the pole. These patterns are old, older than human memory, and they'll be here long after we're gone. But right now, in this moment, they're yours. You get to see them, feel their ancient light on your skin. Know that photons from those stars traveled for years or centuries just to reach your eyes tonight. That's connection. That's being part of something vast and patient and ongoing. The universe doesn't rush. Stars burn for billions of years. Galaxies drift for eons. Light travels at its own pace, and you're here, part of that slow, cosmic rhythm. Your atoms came from stars. Your body runs on energy from the sun. You're made of space. You're made of time. You're made of the same stuff as everything out there. And that makes you home. Not separate from the universe, but woven into it. A temporary arrangement of ancient atoms that became aware, that learned to look up and recognize the place it came from. Tomorrow, the sun will rise. 8 minutes after its light leaves the surface, it will arrive here and warm your face. The moon will continue its slow drift away from Earth, patient as always. Planets will orbit, stars will burn, the universe will expand. All of it following rules set in motion at the beginning. All of it moving at cosmic speeds toward cosmic ends. But none of that requires your worry. You can let it happen. Let the universe do what it does while you rest here, under your small patch of sky, connected to everything. The silence of space surrounds you. The patient deaths of distant stars continue. Your stardust atoms hold you together for now. The moon drifts, light travels, Earth sits in its perfect spot, and you float through it all, carried by a planet orbiting an ordinary star in an ordinary galaxy. You're exactly where you need to be, under the same sky, part of the same cosmos, home. Thank you for taking this quiet journey through space with us tonight. If these calming facts brought you peace, we'd love for you to subscribe to Simple Science for Sleep. Every night, we explore different corners of science, always with the same gentle approach. Made for rest, made for wonder, and we'd love to hear from you. Drop a comment telling us where you're listening from and what space fact helped you relax the most. It's beautiful knowing we're all under the same stars, scattered across the planet, finding peace in the same cosmic truths. May your dreams be as vast and peaceful as the universe itself. Sleep well.